First, let us finish up the peroxide form, how to prepare the peroxide as well as what are the reactions from. Okay, yeah, right. First, let us see a few preparation reactions. Mainly, when you take barium peroxide and add it with H2SO4 cold, then we will see it form barium sulfate and peroxide is released. This is typically how peroxide is being made. While if you take H2SO4 in a concentrated amount, H2SO4 in concentrated amount, yeah, or even if it is warm, in that case, it will become BaSO4, but at the same time, this will undergo decomposition. So H2 plus half O2. So separating it as a peroxide becomes challenging for this. Got it? In fact, barium sulfate is a white PPT and it forms a layer around the barium peroxide, which also reduces the rate of the reaction. Correct? So preferred form of preferred form of barium peroxide is BaO2.8H2O. So when you have hydrated barium peroxide, then that precipitation and getting a layer on the surface will be avoided. That's why this is more preferred way. Okay. Second thing is H3PO4 is relatively more preferred. Okay. More preferred than H2SO4. Okay. So typically you will see barium phosphate is also insoluble and there is no issue with that. And peroxide is extremely stable in phosphoric acid. So therefore, it can be used. BaO2 plus 8H2O plus H3PO4, right? 2 moles here. If I take it this way, 3 moles here, then I'll get Ba3PO4 twice. This is also a PPT plus H2O plus H2O2. That's how we can get peroxide using phosphoric acid. The same can be done even with carbon dioxide. So if you add it to carbon dioxide, it will become barium carbonate, a white PPT. Okay, and peroxide will be released. Okay, these are few methods by which you can do it. Second one is by electrolysis of 50% concentrated H2SO4. 50% concentrated H2SO4. Okay. So here H2SO4 first will convert into H plus and HSO4 minus. Correct. This is almost like 100% ionization. And thereafter, the H plus present will accept these electrons to convert into H2. And this is the cathode reaction, which you will notice. While anode reaction is using HSO4 minus, right, to give H2S2O8 plus 2 electrons. H2S2O8 plus 2 electrons. Got it? And you would notice that because you keep it in the aqueous solution, this will undergo hydrolysis as well. Okay. Due to, due to hydrolysis, you will notice that it will form H2SO5 plus H2SO4. These are the two parts which you will get. And H2SO5, which on hydrolysis will give us H2SO4 plus peroxide plus H2O2. So that's how we will see the peroxide is formed in this whole case. So what are the intermediates that are formed? First, this is disulfuric acid, peroxy disulfuric acid. Then we'll get peroxy monosulfuric acid. And then we'll get sulfuric acid leaving behind H2SO4. Okay. So this is in line how the reaction would take place. Got it? Text. Next reaction is about 2-ethyl anthraquinone. Okay, 2-ethyl anthraquinone is this one, where we have three rings connected with each other this way, here, like this. And we have, let me put the structures properly, like this. Okay, now this, if you have anthraquinone, that is OH and OH here, clear? And this when you treat with O2, this when you treat with O2, so then you will notice that it will become double bond O, this way plus peroxide, H2O2. Okay. This way, in the presence of O2, you will see H2O2 will be coming across. Okay. This is 2-ethyl. Array. I didn't mention where is ethyl. So ethyl is here. Ethyl is here. So this is called 2-ethyl anthraquinone. Okay. In laboratory, how it is prepared is by using K2S2O8, right? That when you treat it with D2O, you will get 2 moles of K2SO4 plus D2O2. This is one way of preparing heavy peroxide. Clear? This is preparing heavy peroxide. Okay. Properties wise, properties of peroxides, peroxide wise, if you notice, right, it is colorless liquid. Peroxide is colorless liquid. Okay. And it is miscible in water, as well as it will undergo crystallization, right, when it is forming a hydrate, that is crystallizes crystallizes uh, to form hydrate, that is H2O2 dot H2O. That's how the hydrate is being formed. Okay. It is a weak dibasic acid. It is weak dibasic acid. Okay. And it will have larger hydrogen bonding. Okay. And can be act as possess hydrogen bonding, possess H bonding, and act as both oxidizing and reducing agent. Both oxidizing and reducing agent. Okay. And that will happen in both acidic and basic medium also. So first let us see acidic medium. In acidic medium, how does it oxidize? And finally, what are the reactions which will take place? So H2O2 has the ability to form H2O and provide nascent oxygen. And this is that nascent oxygen which will help it to get oxidized. Okay. So suppose if you take H2O2 and if H2O2 is passed through all of these compounds like PBS, okay, lead will get completely, sulfur will get completely oxidized to become PbSO4. Okay. Next, if you have H2S, H2S will form colloidal sulfur and I minus will form I2, NO2 minus, NO2 minus forms NO3 minus, got it? SO3 2 minus will form SO4 2 minus, ASO3 3 minus will form ASO4 3 minus, got it? Now if you have K4 FeCN6, that will convert into K3 FeCN6. So oxidation state of iron changes from +2 to +3. Alright, so it changes from +2 to +3. Next, if you only have NH2OH, it will convert into HNO3. These are all the cases where it is acting in acidic medium. It is acting like a oxidizing agent. Okay, in alkaline medium, how does it act like an oxidizing agent? Okay, basically, you think this way: if you have chromium +3 and you treat with peroxide in alkaline medium, that is OH minus, it will convert this into CrO4 2 minus. Similarly, if you have Mn plus 2, right, plus H2O2 in the presence of alkaline medium, OH minus, this will also convert into MnO2. This will convert into MnO2. Got it? Now, whatever cases we have seen, this is all acting like an oxidizing agent. Got it? So, in same, now H2O2 as reducing agent, H2O2 as reducing agent. In reducing agent, we expect that H2O2 to get oxidized to O2. It has to convert into O2. Okay. So again, we'll see it in acidic medium as well as in basic medium. See, H2O2, if you been treated with KMNO4, KMNO4 in acidic medium, this will convert into Mn plus 2 plus O2. Got it? Now, same way if you treat with MnO2 in acidic medium, it will convert into Mn plus 2 plus O2. If you have, HOCl in acidic medium, it will convert into HCl plus O2. Got it? In all of these cases, it is acting like a strong oxidizing agent. Same way, in basic medium, if you notice, H2O2 in basic medium, that is in alkaline medium. So in alkaline medium, in which cases what will happen? Let's see. Suppose if you take H2O2 in basic medium, then if you treat with Cl2 in the presence of OH minus, Cl2 will get reduced to become 2Cl minus. Okay. If you have KiO4, so it will become KiO3. And if you have Ag2O will get reduced to Ag here. And if you have Fe plus 3, that it will convert into Fe plus 2. And same way, if you have complex, that is K4FeCN6, right? Sorry, K3, K4, K3. So K3FeCN6, so it will become K4FeCN6 because now iron is getting reduced in this case. Clear? So these are few cases you need to learn, like in what case what will happen. Okay, this is the important area from peroxide, right? As an oxidizing agent, as a reducing agent. This as oxidizing agent, as oxidizing agent. Okay. Now, in short, two reactions which are always very confusing and that has been asked will be this one. That is how Fe plus 2 changes to Fe plus 3. Okay. So if it is from Fe plus 2 to Fe plus 3, that means this is peroxide in H plus. Okay. If it is the other way around, that means it is peroxide in OH minus. Clear? Same is the case with Mn plus 2 to MnO2. That is in peroxide in basic medium. Clear? And MnO2 to Mn plus 2. That is in peroxide in acidic medium. Clear? And lastly, iodide. So I minus. I minus to I2. Same thing from here to here. Peroxide in acidic medium. And I2 to I minus. Peroxide in basic medium. Okay. So you can see these three are to be interchanged. Clear? What are the test for peroxide? One thing, it will convert One thing, it will convert any form of chromate, that is Cr2O72 minus, when you add it with H2O2 in the presence of any ether as a solvent, then first it will become a blue color liquid. Blue color liquid. Got it? And CrO5 will have a peroxy linkages here like this. It will have a peroxy linkages. This is the blue color liquid form. Got it? Second, peroxide will convert, any form of PBS, right? Clear? Into, this is black color, into PbSO4, which is white color. This is again another confirmation. Third and main confirmation is about giving a titanic acid, that is Ti plus 4. If you treat with peroxide H2O2, then it will give us H2TiO4. H2TiO4. Okay. And here, this is not any redox reaction. Okay. It is just going to give it this way. So basically, titanic acid will be like this. So there is a peroxy linkage. So simply peroxide got connected to it. That's it. Okay. But the oxidation state has not changed. Clear? So what would happen is Ti plus 4, which is colorless, will become an orange color. Orange color that gives a confirmation. Okay. I hope this part is clear. Okay. Next, H2O2 decomposes easily, decomposes in dust. Any form of dust, it will happen fast. So dust is a catalyst for decomposition. All alkalis, any alkalis if you have, or glass, right? If you have metal ions are present, okay? MnO2, etc. All metal surfaces, etc. Okay? And H2O2 stabilized in, or rather, it will be stable in urea. It will be stable in urea, glycerol, H3PO4, or Na2, SNO2, stannate, SNO3, stannate. Clear? And stored in plastic bottles. And these compounds are called inhibitors, inhibitors, stabilizers or inhibitors. And so this is the brief synopsis of peroxide, guys. These 2 pages, I would request you to just go through once. Clear, everyone? This is all you need to learn it from group 16. Now let's quickly go through group 17. Right, let's talk about group 17 now. In case of group 17, okay, uh, first we'll browse through all the elements, what is their properties, and most important area here is about mainly reactions of chlorine, right? What are their acid reactions, as well as uh, mostly to do with interhalogens. Okay, so let's see. Let's start off from here. These are the elements. These are non-metals, and astatine is radioactive metalloid. Metalloid. Here. Next. General configuration is NS2NP5 here, and they all show non-metallic character, and that decreases down the group here. F2 is a pale yellow color, Cl2 is greenish yellow, bromine is red liquid, iodine is black solid. And as the size increases, with increasing the size of X2, physical properties changes from gas to liquid. Okay. And this will become more solid. And this the reason for that is London forces or van der Waals forces. Got it? And I2 conducts electricity to a small extent in solid state and liquid state, and conductivity increases on increasing temperature. Okay. In gaseous phase, F2 is a pale yellow, this is greenish yellow, reddish brown, and violet. Iodine will become violet color. Okay. In gaseous state. Now, if you notice, color of X2 is due to the HOMO-LUMO transition of electrons by absorbing radiation. So if you check out the last orbital of fluorine, that is pi star 2px2 and pi star 2py2. So the electrons from this pi star will jump into LUMO orbital, correct? From HOMO towards LUMO orbital. Acha, what is a LUMO orbital? Sigma star. Sigma star 2pz is a zero electron, so that is LUMO. So this jump is what we are expecting it to happen. Okay. And usually the gap between these two energies is more for fluorine. And the gap keeps decreasing. You can see this is the gap, energy gap. Energy gap keeps decreasing as you would notice towards iodine. So you'll notice that the wavelength required here is less. That means the energy required for the wave should be more to jump from HOMO to LUMO. Here the energy required will be lesser. It required is less. So that's the reason why the coloring is. So by the time it comes to violet, that means the energy required is at a which very low amount. So the complementary color will always be violet. Okay. Next. Clear? Next. Going down the group, if you notice that the, what we say, what are the properties we need to check? Let us understand that. Atomic size wise, it will increase. Ionization wise, it will decrease. Electron gain enthalpy wise, there is a slight difference between chlorine and fluorine. Okay. Right. Another thing that might be asked, I'll just mention it here itself. In the solvents, for example, if you have some donor atoms, correct? Some that means there is some lone pair carrying groups in that case in solvent. Then also there is a slight change in the color. Correct? Right. For example, okay, if you notice that iodine, okay, if you take iodine in CCl3 or CHCl4, clear? CCl4. Here, this will be appeared as violet color. This will be appeared as violet color. Got it? But hydrogen in, you know, any hydrocarbon which will have a donor ability, like benzene will have the pi bond, which will have donor ability. In that case, it will become pink or reddish, pink or reddish brown. Got it? So if you have donor ability, the color will become more and more deeper. So that is I2 in the presence of uh, alcohol, ethers, pyridine, correct? They all will have very strong donor, which is lone pair. Lone pair is a strong donor. So in that case, it will be deep brown color. Brown. Okay. So all you need to, it's not that you have to mug up the colors. You just need to know that as the donor nature changes, the color will also change. Okay. And if you compare the solubility will be more when it is having a more donor groups. Clear? So I2 solubility, if you notice, solubility, then it will be more in alcohol as compared to that of CCl4. Why? Because ROH has a donor lone pair. So if you have a donor lone pair, the solubility will be always more. Clear? Right. Next. Check out boiling point and melting point. Iodine, bromine, chlorine, fluorine, a regular trend. Down the group, it increases. This is an important area, that bond dissociation area is greater for chlorine, bromine, and than fluorine. Fluorine will have very strong electron-electron repulsions, because of which breaking the bond is easy. See, bond length is smaller, but the energy required to break is, lesser as well. So keep that in mind. So fluorine would be this way. Okay. Next. Bond length wise, if you notice left to right, it increases. Okay. Fluorine will have the smallest bond length here. Okay. Next. If you notice oxidizing power for this one. Okay. If you notice the oxidizing power for this one, oxidizing power mainly depends upon uh, how much amount of ability it has to form, you know, as the aqueous ion. So, for example, if it comes to fluorine, just write down that here. If it takes to fluorine as a gas from here to convert into F minus aqueous, then what are all energies it will go through? First, it will go through 2F gas, then it will become 2F minus uh, gas, and from here it will become this one. So here it is a bond dissociation energy, and here it is, uh, two times of electron affinity, and here it will be two times of delta H of hydrogen. So some of these three factors will decide whether it will act like a good oxidizing agent or not. Okay. Check. So in case of F2 and Cl2, delta H of vaporization and delta H of fusion are not much involved. Correct. So though, I mean, if you notice, overall oxidizing power, mainly it has to do with the hydration. Very high hydration of F2 is the one which will help it to have stronger oxidizing potential. So that's why F2Cl2, you will notice F2Cl2, Br2 and I2 is the right way of looking at it. Which means F2 can literally oxidize anything. So Cl minus it can oxidize to Cl2, and anything. Br minus will also get oxidized. I minus will get oxidized and so on. Now, within chlorine here, if I write the reduction potential here, first you will come across fluorine, then O2. And then when it comes to chlorine, bromine, and iodine, you'll notice that chlorine would be more, then bromine, then iodine, and last comes ClO3 minus. ClO3 minus is not very strong, reducing group here. Okay. So you will see here KClO3 plus I2 will become Cl2 plus KiO3. KBrO3 plus I2 will give you Br2 plus KiO3. Okay. So mistake. I2 is getting oxidized. ClO3 minus is getting reduced. Bit wrong here. So Cl2 is more than ClO3 minus and I2. Because I2 is getting oxidized easily and ClO3 minus is getting reduced easily. Yeah. Yeah. Okay. Next, check out the oxidation states here now. Fluorine showcases -1. Chlorine, bromine, iodine goes anywhere from -1 to +7. Okay, these are all the oxidation state which are being observed. Okay. Chlorine and bromine shows +4 and +6 in their oxides, correct? So these two are the oxides where it can show +4 and +6 in this case. Clear? And the higher oxidation state in case of bromine is less stable. Okay. Bromine does not show much of higher oxidation state, and plus 7 oxidation state is very rare for bromine. Okay, and this is called as middle row anomaly, and we discussed the same thing with selenium if you recall. Okay, next see the reactions here. First with H2. F2 plus H2O will give you HF plus O2. Okay, and the same thing will go, but some amount of O3 will also be formed. Okay, so F2 is such strongly oxidizing, it will even form some amount of O3. So what we get is ozonide oxygen. Chlorine disproportionates in water becomes HCl and HOCl. And HOCl, if you keep it for long standing, again loses the nascent oxygen that will convert into O2. So Cl2 plus H2O can be used as a bleaching agent. Next, Br2 and water, if you notice, will become HOBr and HBr and HOBr. I2 in water has no reaction. Solubility generally is F2 towards I2. This is how the solubility changes. Okay, clear guys? Next, one minute. There is one change here. Correct this. Solubility will be F2 will be more soluble. Okay. Then comes Br2, then Cl2, then I2. Okay. Typically, solubility in water will be like this. Okay. See, it will undergo slow disproportionation. Bromine will undergo slow disproportionation. But as much as the solubility is concerned, bromine is relatively more soluble than chlorine. Got it? It has to do with how much amount of van der Waals forces it can make with water. Bromine can make very strong van der Waals forces, but at the same time, it will have some amount of hydration also. With iodine, although the van der Waals forces are strong, there is very least amount of hydration here. So breaking this becomes a challenge. So that's why solubility of I2 will be lesser. So, but remember the order here F2, Br2, Cl2, and I2. Next. Check out the reactivity with NaOH. F2, when you react with NaOH, cold and dilute, then it will become NaF, OF2, and H2. Oxidation state of fluorine is not changing. This is not a disproportionation reaction. Got it? Next, NeX2, if you react with NaOH cold and dilute, it will become X minus and XO minus, XO plus 1. Okay, XO will be at XO minus will be having oxidation state of halogen as plus 1. And if you use hot and concentrated, then we'll get X minus and XO3 minus, where oxidation state of halogen will have plus 1. Okay. Next, you see reaction with non-metals. Okay, what is the reaction with non-metals? So B plus X2 becomes BX3. Phosphorus plus X2 becomes BX3. If you add excess, it will go up to X5 also, except iodine. S plus F2 will become SF4. S plus Br2 will become S2Br2. With excess of fluorine, it will become SF6. S plus Cl2 will become S2Cl2 or SCl4. Next, what are the reactions with metals? Metal with F2 will become MFX. Cl2 with Br2 will become, MClX and BRX. Iodine with metal, any one except noble metals, then you'll get Mi. You'll get this as Mi formation. Done. So I hope this part is clear, everyone. Next, with halogens, I think I have to give the reaction with H2 also. I forgot that. Um, reaction with H2. Reaction with H2. That is H2 plus F2. H2 plus F2 will completely convert into 2HF very easily. Clear? It's very stable. So in dark medium also, that means it is a very, very powerful or strong reaction. Next, H2 plus Cl2. If it is H2 plus Cl2, then it will become 2HCl. Then it will become violet. That will be violet colorish. Next one is H2 by Br2, H2 plus Br2, and this is around 300 degrees centigrade. Will give you 2 HBr, and H2 plus I2, 440 degrees here. So to make this as 2HI. So these are the reactions which you'll see with H2. Now, coming to the hydrides, okay, how does the hydrides are formed here? See, when it comes to hydrides, HF, HCl, HBr, and HI are present. Bond dissociation energy wise, if you notice, so we'll have HF greater than HCl, HBr, and HI. Acidic nature wise, if you notice, down the group acidic nature increases, reducing nature increases, thermal stability decreases. Delta H of vaporization, will be more for HF than HI, HBr, and HCl. Melting point will be more for HI, HF, HBr, and HCl. Boiling point will be HF greater than HI. And dipole moment will be more for HF, HCl, HBr, and HI. So please go through that terms once, everybody. Then see. Let us see first with, preparation of HF. Okay. What are there in HF? And I have only first took the part of NCRT what is given. Otherwise, we have to discuss few more important things also that I'll discuss it as we go ahead. See, CaF2 when you treat with concentrated H2SO4 will give you HF and calcium sulfate. Now, HF in liquid and solid state has zigzag structure. This is the structure which you'll have. Remember that H should be always at the middle, fluorine should be always at the corners. Got it? Right. Next. In vapor state, it will exist monomeric in nature. In dimer, it can exist as dimer and it will also exist as cyclic hexamer. Okay. And it cannot be stored in glass containers because it will react with silica and forms into soluble hydrofluoric acid. Okay. And HF also has a unique property to form salts with F minus. That is, if you take KF with HF, so it will form some kind of a salt as K plus and HF2 minus. Next, sorry. HF also has more K value in concentrated aqueous solution. That is, if you take HF plus water in the presence of K1, it will become H3O plus and F minus. Okay, and HF plus F minus will again become HF2 minus. Therefore, overall reaction is 2HF plus H2O becomes H3O plus HF2 minus. And for this, the K value is greater than that of K1. And guys, right, next. Check out on HCl and HBr. So when it comes to HCl, NaCl plus concentrated H2SO4 will give you HCl. NaCl plus NHSO4 will give you HCl and Na2SO4. HCl is colorless, pungent smelling gas, white fumes with ammonia, can dissolve platinum and silver with concentrated HNO3 taken, what we call it as aqua region. Okay, what we call it as aqua region. And 1 minute, I will add the reactions of HBr and HI also. Okay, in case if it is been asked, so it's better to learn about them as well. HBr reaction same way NABr when you treat with concentrated H2SO4. Clear? Problem here is we will get HBr in a very small amount. Rest of the bromine will get oxidized to Br. So we cannot get HBr easily. That's why what we do is we add it with H3PO4. H3PO4 will not have any oxidizing nature. So therefore, this will become HBr. HBr and NaH. 2PO4. Clear? Similarly, if you have red phosphorus plus Br2, red phosphorus plus Br2, first you know that it will become Br3, PBr3. And PBr3 on hydrolysis, acidic hydrolysis will become H3PO3 plus HBr. This is what you'll get. And next we have HI. So when it comes to HI, we have NAI plus concentrated H3PO4. And then this will form HI plus NaH2PO4. Correct? Just like how we did it for bromine, the same thing can be done here. Phosphorus plus I2 will become PI3. That on hydrolysis will give you H3PO3 plus HI. Done. This is for the preparation of HI. Clear, guys? Now, there is one important thing about HF. Like I said, it will increase the concentration as you add it into uh, sorry, if you keep it in a concentrated amount, the K value will increase. Similarly, okay, note here, if HF is being added to other solvents, okay, like N2O4 or H2SO4 like this, which is non-aqueous solvent, HF in non-aqueous solvent, what would happen? Let us see. Okay. So if you have 3HF here, and it will become H2F plus and HF2 minus. This is how the ionization will take place. And HF to some extent will be ionized into H plus and F minus. And HF plus H plus will give us H2F plus and HF plus F minus is giving HF2 minus. So if I write the overall reaction in this case, so that is 3 moles of HF, 3 moles of HF, and that is going to give us H2F plus HF2 minus. Okay, so you can understand that this equation 1, equation 2, and equation 3 adding, we will get this overall reaction. Clear? Now, this is what happens, right, uh, in non-aqueous solutions. Clear? Right? So therefore, suppose if you are adding HF, if you are adding in a solution of HF, HCl, HNO3, H2SO4, all act as bases. They all act as bases, correct? In pure liquid HF. Okay, only pure liquid HF, not aqueous solution, but HF. Let me show you how. So if I take H2SO4 and add it with 2 moles of HF here, so it will become H2O and SO3H plus. Okay, sorry, plus is here. Plus HF2 minus. So it will become HF2 minus. Okay. Same way, if you notice HNO3 plus 2 moles of HF, it will become H2NO3 plus HF2 minus. So that's how these are generally acid, but when you add it to the pure liquid HF, this is what you'll notice. Correct? While if you have HClO4, HClO4, you know, FSO3H and BF3, ASF5, PF5, SBF5, they all remain acidic. They all remain acidic in this case. Okay. Let me show with an example. HClO4 plus 2 moles of HF will give us H2F plus ClO4 minus. Now you can see HF is taking that H plus from here. Got it? Same way, if you take BF3 plus, HF. So here you will see this will become BF4 minus plus H plus. That's how it is, observed. In fact, so much so that SbF5 plus HF is extremely acidic. That is SbF6. So this is called as superacid. It is called as superacid, extremely acidic in this case. Done, guys. So keep this in mind. So in case if it is HF as a pure solvent, what all things will act like bases, which all things will act like acids. Okay, right. Now let us come to HCl preparation. I think, sorry, I told you about the HCl preparation. No. NaCl, it will become HCl. This will also become HCl, white fumes, and it will dissolve platinum and gold. Correct. And what are the other factors we should need to know? Correct. See, HCl HCl has been used in identifying the basic radicals, sorry, acidic radicals, HCO3 minus, SO3 2 minus, S2 minus, CH3CO minus. Yes, so that is one thing you should know where it is used. Next, oxides. Oxides wise, if you notice fluorine, chlorine, bromine, iodine, fluorine has only two oxides, OF2 and O2F2. Chlorine has this bunch of oxides, Cl2O, ClO2, Cl2O6, and Cl2O7. Bromine has Br2O, BrO2, BrO3, and Br3O8. Okay. Iodine has I2O5, I2O7, and there are two other iodides which are completely ionic oxides. Right. So if you notice that uh, delta H of formation, okay, here I have written the oxides of chlorine are not prepared by oxidation of chlorine. It is not by just simply oxidation of chlorine, as delta H is always positive for them. So those reactions will not happen. Except, these all reactions, Cl2O, ClO2 will not happen. But except if you give Cl2O7, I mean, to formation of Cl2O7, this is going to have delta G of the reaction. Delta G of the reaction negative. This will have delta G of the reaction negative. Correct? I guess this part is clear. Only for Cl2O7 it is negative, but all others are delta uh, delta H delta GF will be positive. Okay, and notice these ionic compounds. I4O9 is I3 plus IO3 minus, thrice of it, and I2O4 IO plus and IO3 minus. Okay? These two are completely ionic forms. And you know the structure of Br3O8. Okay, that is another important one which you need to remember. Br, Br, and Br, they are interconnected like this: double bond O, 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 like this. This is all Br3A. So now, if you check out the oxidation state here also, it is +6 on both corners, and it is +2, right? +4 on uh, +4 in the bromine inside. Clear? So this is a completely covalent molecule. Correct? And wherever the star mark which I have written, these are all paramagnetic in nature. Correct? Next. Yeah. Now check it out. When it comes to stability wise, you will notice that iodine will have more stability because they will have ionic compounds ionic compounds are formed here as compared to that of chlorides, right? As compared to that of bromides, correct? So most of the oxides of iodide are very stable because of uh, ionic compound formation, correct? Right. Now let's see what are all the oxides here and how they are prepared. First one is Cl2O. Cl2O, when you add it to water, it will become HOCl. So which means Cl2O can be considered as anhydride of hypochlorous acid. Cl2O is an oxidizing agent, and Cl2O, when you add it with ammonia, will release N2 gas and HCl will be formed here. Got it? And Cl2O here, if you notice the structure wise, we have OCl here, and that will possess a back bonding. Okay, that will possess a back bonding. And the bond angle due to back bonding is coming close to 111 degrees. Okay, this is the back bonding. This is the bond angle for OCl2. Got it? Then it will act like an oxidizing agent. I hope you got an idea what exactly the reactions are happening. Next, one more simple reaction within that. Okay, I'll just mark it down with another color here. See, if you take Cl2 plus HgO, okay, this is how you make HgCl2 dot HgO plus, Cl2O will be formed. Got it? And this Cl2O, if you add it with water, and that will give you HOCl. So just keep that in mind. So when you connect with HgO, this is what has been formed, and some amount of Cl2O minus will be released. Right? And if you notice what are all the reactions of okay, first I'll do one thing. Let me just go through a briefing of Cl2O, ClO2 and all of that. Then we'll do the reactions. I think that will be better. See, ClO2 is yellow color gas. It will have this structure. This electron, which is present on oxygen, will keep moving around two oxygens, and it will not have any ability, because it will continuously move around these spaces. You will not see it will have an ability to dimerize. So that is why ClO2 will not undergo any dimerization. Guys, clear with that? ClO2 does not undergo any dimerization. Okay. And ClO2 is a mixed oxide. That means when you add it to water, it will become HClO3 and HClO2, mixed oxide. Next is Cl2O6. It is a red color liquid. Cl2O6 is a red color liquid. And uh, when you add it to water, it will become HClO3 and HClO4, which makes it also mixed anhydride. So Cl2O2 is also a mixed anhydride. Lastly, Cl2O7, it is a colorless liquid, and when you add it with water, it will become HClO4. It is a simple anhydride of HClO4 here, and HClO4, when you treat with P4O10, it will give us Cl2O7. So that is a preparation of Cl2O7. Okay. And one reaction of Cl2O7 which we need to know is that uh, I think we have written it already. No, it's okay. Got it. So in case if you react it with NaOH, it will become NaClO4, obviously, because it is an acidic salt. Because it is an acidic oxide, it will become HClO4. Reaction with NaOH will become NaClO4. Got it? Right. So I'll give you few reactions of this 1 minute. I'll just check out where I can put it here. So I'll add few reactions here. Check. Reactions of, okay, oxochlorides. Just remember directly as reactions, okay? You don't need to worry about which particular case it is. So just remember it directly. So first one, if it is given as Cl2O with NaOH, we just learned that Cl2O is an anhydrous of HOCl. So that will become NaOCl plus H2. This is reaction number one. Second reaction. Clear? Now, if you have NaOCl, right? Sorry, if you have NaOCl here, correct? Uh, huh. If you have NaOCl here, that when you treat it with OH minus again and heat it strongly, so then it will get disproportionated to become Cl minus and ClO3 minus. Cl minus and ClO3 minus. Correct? And if we pass this ClO3 minus in the presence of, barium, then this will convert into a barium and H2SO4. So this will become barium sulfate, and thereafter it will become HClO3. So barium 2 plus. Then this is reaction number 3. Next. Next, if you take ClO2, same reaction here again, Cl2O plus NaOH, I mean ClO2, sorry, ClO2 plus NaOH. It is a mixed anhydride. So since it is a mixed anhydride, we can expect this to, give reactions as NaClO plus NaClO3. Clear? O2 and O3. NaClO2 and NaClO3. Got it? Next is which reaction? Yeah. If you have this reaction, check out in this reaction. NaClO3, okay, plus 2 moles of H2C2O4 oxalic acid. This will give us carbon dioxide plus ClO2 plus Na2C2O4. Okay, this is one way used for preparation of ClO2. Okay, another way is instead of using this, I can also use it as NaClO3 plus SO2 plus H2SO4. So in that case also you will get this as ClO2 plus 2 moles of NaHSO4. Then next, another reaction which you need to know, that if you have ClO2 and you treat that with peroxide H2O2 in the presence of NaOH, so it will make that oxide into O2, and this will convert into NaClO2, which if you add it to H plus, it will become HClO2. So that's how HClO2 can be separated. Okay, that's how this can be separated out. Okay, so that's it. These are a few reactions we need to know from oxochlorides. Coming back to this oxo acids, check out what are the oxo acids we have. When it comes to fluorine, fluorine will have HOF, which is again unstable form. So HOF is the only acid we can expect. Next, HOCl, HClO2, HClO3 and HClO4. Remember the names: hypo, chlorus, chlorus, chloric, and perchloric acid. Acidic strength wise, HOCl will be greater than HOBr and HOI. Okay. Stability, this is to do with the stability because it will make 2p, 3p overlapping, 2p, 4p, and 2p, 5d overlapping. So obviously basic nature wise, IO minus is more stronger base. Next, this is one important exception. So when it comes to HClO3, HBrO3, and HiO3, sorry, not this one, the next one. HClO3, HbRO3, and HiO3. You will notice that ClO3 minus will have again better overlapping than this one than this. Okay, that is how the acidic character. Clear? So if you notice the acidic character of HClO4, again HClO4 will be greater than HbRO4 and HiO4. Got it? Now, if you notice the acidic strength for HClO4, this will have more resonating structure, so this will have more amount of acidic nature. Now, another problem here is this will have more resonating structures. That is the reason why this is more acidic. But at the same time, if you notice the bond order is highest in the case of ClO4. That also make it thermally stable. So thermally more stable is also HClO. Okay, so keep that in mind. Thermal it is more stable as well. Next, oxidizing nature: HOCl, HClO2, HClO3, and HClO4. It will decrease down the group. See, it is because these are very stable ions, so they can release out H plus more easily, but not nascent oxygens. Nascent oxygen wise, HOCl will release better as compared to the of HClO2, HClO3, and HClO4. Right. Next, if you notice HiO4, which you call it as periodic acid, which exists as HiO4 dot 2H2. Okay, and usually it is being written like this: H5, H5, IO6. This is what we have. We usually write. Okay. Next. Sorry. As a reaction, if at all I have to give, this is the reaction that will take place. That is uh, HiO4. Clear? HiO4 here. When, sorry, if I take this as H5, H5IO6 here, from here I'm talking about. This, if at all I heat around 100 degrees, so water molecules will go away and that will become HiO4 first. Okay. And this HiO4 on heating will give us, I2O7. This plus H2O. And I2O7, if you heat further, it will become I2O5. It will become I2O5. And you know that I2O5 is used for estimation of carbon monoxide as a reaction, very important quantitative reaction here. I2O5 plus 5 moles of carbon monoxide will give us, I2 plus 5 moles of CO2. I2 plus 5 moles of CO2. Okay, done. Next, check out interhalogens. XX dash, XX3 dash, XX5 dash, and XX7 dash. These are the interhalogens. Chlorine, bromine, iodine. These are the forms which you will see for fluorine. Okay. So if you notice all the monoforms, these are all the monoforms which we have here. I forgot to put a mnemonic. I'll just add on a mnemonic to that. Okay. So colorless, these three are, you go from left onwards. All fluorines, if you have noticed, they are all colorless. Whenever there is fluorine with chlorine and iodine, they are all colorless. And with bromine, these two are colored. This is colorless. Hello. Sorry, check it out. So these are basically colors of interhalogens. Okay, mainly the colors which you will be asked are these. Okay, these are the ones which have been known, and whatever which I marked, please learn that. BRCl is red brown, IF3 is yellow, ICl3 is orange, ICl is red, and IF7 is colorless. Okay, so these are mainly the colored ones which you need to know. Clear? Right. And you see, all these interhalogens are covalent in nature. These are all covalent in nature. Let me just add on that first. All interhalogens, all interhalogens are covalent in nature. Okay, and all are diamagnetic. All are dia, all are diamagnetic in nature. Correct. Right. Next. So if you notice the reaction wise and preparation wise. Okay. So I'll just give you an idea about that first. So in the same sheet, you can see reactions preparation wise, preparation reactions. Okay. So if you take Cl2 and F2, Cl2 and F2, then it will form ClF at around 200 degrees Celsius. Okay. The ratio should be 1 is to 1. If Cl2 plus F2, this is in excess. If this is in excess, then it will form ClF3. Got it? And ClF3 plus F2 is given, then it will become ClF5. Got it? Br2 plus F2. Br2 plus F2, it will become BrF3. BrF generally is not formed easily. Got it? And if we take F2 in excess, then it will become BrF5. This will become BrF5. Next, I2 plus Cl2, I2 plus Cl2 will usually become ICl if it is in 1 is to 1 ratio. If I2 plus Cl2 excess is given, then it will form ICl3 twice. ICl3 twice as in basically I2Cl6. It will always exist as a dimer. I2 plus F2, if you keep it around 250 degrees to 300 degrees centigrade, then it will become IF7. Okay. So IF7 would always form at higher temperatures. Done. So these are typical preparation reactions which you will notice from interhalogens, how they are prepared. Yep. Structure wise, you will see that I mean ClF3 bent T shape, you know, alpha and beta. If you compare, what would happen? IF7, the hybridization and structure. BrF5 square pyramidal. I2Cl6 square planar. Correct. These are all the forms. Okay. And I2Cl6 square planar here. And generally, interhalogens are more reactive than halogens. In general, you'll always find that interhalogens interhalogens are more reactive than halogens. They are more reactive than halogens. Okay. Why? Because it will have more polarity. Due to more polarity. Due to more polarity. Okay. And If you have this x dash here, so then you will get this as, this acids. If you have x dash added to water, x3 or added to water, x5 added to water, x7 added to water, then these are the forms you should have. Clear? Now, one thing you need to notice here while writing the interhalogens, the one which we write it on this side, right? This side will always be more electronegative. On the left hand side, what you will write will always be less electronegative. So you can see the less electronegative ones will always become oxoacids. More electronegative ones will always make hydroacids. Okay. So even if you have that confusion, just keep in mind which one to get it first. Okay. And next you see polyhalogens, polyhalides or polyhalogens here. That is when you have halides reacting with halogens or interhalogens. Correct. If intra halogens or halogens together reacting, then we get polyhalides. So that is I2 plus I minus will give you I3 minus. So that is an halogen reacting with a halide. Or you can also have uh, uh, reactions of, what do you say, halogens reacting with another type of, what do you say, one type of halide reacting with the other type of halide. That is also an polyhalide formation. Okay. Now, if you notice that some form of Cl3 minus, Br3 minus are found, F3 minus are never found because they does not have any vacant d orbital. Solubility wise, I3 minus is more soluble, and that stability also, if you notice, ClF plus and I3 minus, that will be strongly ionic, so that will be more stable compared to that of Ki3 and NaI3 and so on. Okay. Now, few important reactions from here, what you need to know is this, that if you take, KCl and treat that with ICl, okay, then what we will get here is K plus and ICl2 minus, K plus and ICl2 minus. Okay. Now, this would be linear like structure, I3 minus. Correct. Next, KCl plus ICl3, if at all I react with that, again it will become K plus and ICl4 minus, ICl4 minus. And similarly, KCl plus IBr, if at all I react, clear? So then this will become K plus and IBrCl overall minus. Now, important point here is when these polyhalides are heated, right, it will form again a metal halide, which will consist the smaller halogens due to the strong lattice energy. So suppose if at all I start heating it here back, which halide I can expect? I can definitely expect KCl to come out, correct? And rest will become IBr. Same lines, if any compound is given to you, that RB, let's say RB, I gave you F, CLI is an interhalogen. And this on heating, I'll definitely get RBF as a major product and ICL will be formed. Okay, so this is important. So remember, okay, smaller size anions will form, you know, metal halides, metal halides due to strong lattice energy. Clear? This is another important. Clear? Lastly, what we need to learn is pseudo halides. Pseudo halides. Okay. Now, pseudo halides or pseudo halogens are the ones which are generally linear and contains at least one nitrogen in it. Okay. So they are linear and contains at least one nitrogen. Okay. Examples include Cn minus. Okay. Cyanide. Got it? OCN minus. OCN minus, that is cyanide. Clear? Then we have SCN minus. Okay, so that is thiocyanate. Thiocyanate. Clear? SCCN minus. Okay, that is selenocyanate. Selenocyanate. Clear? ONC minus. ONC minus. Okay, known as fulminate. ONC minus is called fulminate. Okay. C is always at the center. Although I have written it as ONC minus, right? C will be at the center. Next. N3 minus. N3 minus is called azide. N3 minus is azide. NCN2 minus. Okay. This is cyanamide. All of them will have very similar rules. Okay. Like that of halides. They all behave very, very similar to that of halides. Clear? Most commonly used pseudohalides, most commonly used pseudohalide being cyanide, CN minus. Got it? In fact, if you notice some reactions also, suppose if you take Cu2 plus I minus, then what do we get? We will get this as Cu2I2 plus I2, and Cu2 plus Cn minus will form Cu2Cn2 plus Cn twice. Cn twice is called cyanogen gas. Cyanogen gas. Got it? This is one way of reacting. Same way, AgNO3, if you react with any halogen, I will get AgX as a precipitate. And if you react with cyanide also, I will get AgCN as this white PPT. So that is also a similar form of it. Clear? Forms similar complexes. Forms similar complexes also. Like if you take CuCl4, 2 minus, you will also have CuCN4, 2 minus. Okay. In a very similar way, this has also been formed. Clear? Now, if you have Cn twice, SCN twice, these kind of forms, which are like X2, right? Which are like F2 and Cl2 form. These are called pseudo halogen gases. These are pseudo halogen gases. Clear? Lastly, disproportionation. For example, if I take Cl2 here and add with OH minus, if you recall, it will undergo disproportionation as Cl minus and OCl minus. Similarly, if you have cyanogen with OH minus, if Cn twice, then we will have Cn minus with OCn minus. Cn minus and OCn minus. Clear? If you have uh, interhalogens, we can also forms pseudo interhalogens. Pseudo interhalogens. How does pseudo interhalogen looks like this? Br and Cn. Okay, this is one interhalogen. I and Cn interhalogen. Cl Cn interhalogen, and etc. These are the forms which you can get. Clear? Lastly, if you have something like KClO3 plus HCl, right? If it gives 1 mole of Cl2 and uh, 2 moles of ClO2, 1 mole of Cl2 and ClO2 plus KCl and H2O. This is what is being formed. Well, here basically we will have this as 2:1 ratio of ClO2 and Cl2, correct? And this ratio is called as euchlorine. This is called euchlorine. This is one of the products, I mean, one of the compounds that is always asked in JEE mains before. I mean, I'm not sure if it is being asked again, but yes, this was asked before. So I think you should be able to learn it out. Clear, guys? These are all about the pseudo interhalogens as well as one important reaction here. I'll add this reaction back to that reactions sheet also here. This is one important reaction sheet, guys. Okay, right. So we'll end it here. Okay.